So it's a great pleasure for me to introduce Professor Elena Celledoni. Professor Celledoni is an Italian mathematician from Norway. She's a professor of mathematical sciences at the Norwegian University of Science and Technology in Trondheim. Well, I know Trondheim since a long time because there is a strong soccer team. Before knowing about the university, I knew about a strong soccer team, Rosenborg, which played in Champions League for many years. And now it's a few years that doesn't win the title in Norway. But so a research field of Professor Celledoni is in numerical analysis and structure perceiving algorithms for differential equations and geometric numerical integration. It's actually a very important topic for the type of problems that Katrina and myself are interested in. Before becoming a faculty member at NTNU in 2004, I think, she was postdoctoral fellow in Cambridge at the MSRI Institute, Mathematical Sciences Research Institute, and later on at NTNU. She received a master's degree in Trieste, where actually I did my Ph.D. And she had a Ph.D. in computational mathematics from University of Padua. She had a postdoc position, as I mentioned, in Cambridge, but also at MSRI, but Berkeley and NTNU. So Professor Celledoni is a member of the Royal Norwegian Society of Sciences and Letters. She's a member of the European Consortium of Mathematics Industry Council, a member of the board of the International Council of Mathematics in Industry and Application, member of the editorial board of many journals, CM Review, Network Center, Genius Media, Calculo, GCD, JGM. It's a great time actually to have a speaker from Norway, given that yesterday the Abel Prize was awarded. Well, 600 kilometers, probably 1,000 kilometers of distance from Trondheim, but Abel Prize was awarded to Professor Caffarelli, who's a big expert in partial differential equations. And well, without further ado, I would like to thank Professor Celledoni for being here and presenting her research to us. Thank you very much.
Thank you very much, Alessandro. I'm not used to this kind introductions. Yes, thank you also for mentioning the Abel Prize. We are very proud of the Abel Prize here in Norway, even if it's not really my area, but still it's a nice time. We had cake yesterday, just to tell you, at the department. It's like this. Yes, thank you for inviting me. I'm trying to do my best to sort of say something interesting for several people. I hope this will meet the standards of this seminar. So the topic is shape analysis and with some connections to deep learning, but I'm not sure that there will be much deep learning today. I'll try to mention this connection. And I apologize, I have at least I see one spelling error in the name of my colleague, Helge Glöckner. There is an L missing. So this is joint work, mostly joint work with Helge Glöckner, Jürgen Rieset, and Alexander Schmeding. And Jürgen is the person who has done most of the experiments. And Helge and Alexander are experts in infinite dimensional Lie groups. And I'm the middleman, the one who's making the connection. Okay, let's see. So I will start with some motivation. I will spend the first part of the talk with that, showing some of the applications I have in mind, which hopefully are also interesting for this audience. And then I will go more into the formalities or formalism of the problems and methods which I'm considering. And then I will present a new method or a recent method that we have tried to analyze and to test also with some numerical examples. I will show these numerical experiments. They are not really into applications. They are more like, proofs of concept for the moment. And then I will also give some discuss briefly perhaps some theoretical results, if time permits. So the topic is shape analysis. So what are shapes? Shapes are, just to describe them in words, unparameterized curves or surfaces, at least in this talk. And they can have take values both on vector spaces or on a manifold. A very typical example is this of object recognition. The application, you'd say it's that of object recognition. You have some objects or the pictures of some objects, and you represent these objects by the contours, their contours. And these contours, they are closed curves in particular, but the shape is identified independently on the parameterization of the curve. So this is a quite typical situation. So curves independent on their parameterization. However, these objects, they could also be represented by surfaces. And here it's an example. It's taken from this paper by Yermin. And here what you see is that you have three-dimensional surfaces that represent some object. And what you want to do is to deform one object into another. For example, deform a horse into a cow, or an open hand into a closed hand. And why you want to do such things? Well, for example, because you want to distinguish in between these objects, you want to compute distances in between the objects. So you deform one object into the other, and based on how much effort you're doing, you will say the objects are close to each other or the objects are far apart. And in the case of the hand, open and closed hand, what you could do with this, if you have a good sensible deformation of the closed hand into the open hand, you could create movement this way. So there are good reasons for doing this in a sensible way. Another application, which is at least it was for me quite unnatural or unusual, is this of skeletal animation or virtual character motion. So in this case, we have time curves, so time-dependent curves. And still, they can be treated as shapes, or it makes sense to treat them as shapes. So in particular, what we are doing here is where we are looking at the movement of the skeleton of some character, animation character, for example. And the position of the bones of the skeleton can be represented as rotation matrices in R3. So in particular, we have a reference frame or reference configuration, and the position of each of the bones essentially is determined by one of these rotation matrices. So the configuration space or the configuration manifold of our curve is in fact a bunch of copies of the Lie group SO3. And the animation, or okay, so one position is given by a certain number of these rotations, the position of the character, and an animation is a time curve taking several values in this manifold. So the data which we want to discuss is obtained by motion capturing, and while we have different data points in this manifold or in this setting, what we want to do is, for example, either compute distances in between animations, in between movements, or we want to, for example, manipulate different interpolate in between animations. That's also another possibility. So as I said, the data comes from motion capturing, and here it's a clear example. On the left here we see how the motion can be immediately digitalized through cameras and so on into movement of the skeleton. And we were quite surprised, or I was surprised when my former PhD student, Marcus Essensbrickler, presented this as a possibility of using shape analysis in this case. So he did a paper on this by treating these shapes as curves in Rn. So without taking into account the geometry of the configuration manifolds. And then later on, we did also a work where instead we generalized some of the tools which were very well known for shapes in taking values in Rn. We generalized those two Lie groups. And we were pleased to see that there were some good advantages out of that. So here is a case in which we interpolate in between two animations. So we have on the left, we have an animation of a person or a character who is stepping over an obstacle of a certain size. And on the right-hand side, instead, we have the same person, but is stepping over no obstacle, or the obstacle is very small. So what we want to do is we want to interpolate in between these two animations so that we can create an animation, a new animation of a character which steps over obstacles of intermediate size. And we compare our method with the previously existing approach. And in fact, it is not necessarily so straightforward to make this interpolation in a sensible way. So so we were quite pleased to see that this worked quite well. Another application is, as I said, classification. Yes? There is a question?
Yes, so my question is this: when you do the interpolation, let's say, perfect example, running and walking, by the way, for what I have in mind. So let's say that I want to interpolate with two animation which looks like one running and the other walking. Is there a way to make sure that the interpolation, you go only through motions which are reasonable? Let's say that every of the type of motion that you see during the going from one movement to the other are all reasonable motions. Is there a way to do that?
Well, I mean, I don't think I have a good fix for that. But I can tell you that, yeah, so in part, this is about it, right? So it's to create deformations that make sense, that are feasible or physical, if you can use that word, right? That it makes sense. So it's definitely the goal to achieve this. I think, in fact, what I'm going to say now is that there are several ingredients to have this done. But I cannot tell you that this is the only way or the way to do it, because I don't really know why it works. I just know that it makes sense, and there is a mathematical explanation for this, but not something that really can convince everybody in every applications. I'm not sure about that. But let me try to describe how we are thinking. And here you see we have a classification of three different types of animation: jumping, running, and walking. This is taken from a database. I don't remember It's a database in Carnegie Mellon University, I think. And so we are quite pleased by this clustering of the type of animations that we have, of course. So the result is not that bad. It's quite good, I would say. So we compute distances here in between the animations, and we see that they are clustering very well. So what are the ingredients of our method? And I will go into more details even later. Well, first of all, we respect the geometry of rotation. So we, as I said, the curves, they take values into a manifold. So we respect the structure of the manifold, the fact that we are working with data on a Lie group. But another important feature is that we respect the fact that that we are dealing with shapes and that these curves are reparametrization invariant. So for example, if we compare a running animation with a jumping animation, what do we know? We know that running is different from, running and walking is an easier way of thinking. Running and walking are two different type of movement, but they are not differing by the speed. The speed is immaterial. It's a different movement that it doesn't have only to do with speed. So with this reparametrization invariance approach, what we do is we factor out this effect of speed. Speed is unimportant, and we can compare shapes where the speed is not material, is not important. What do we have to pay for this, or to get this kind of a good result? Or it's a costly optimization algorithm, a costly optimization problem that we have to solve, and we do that by using dynamic programming, at least in this experiment. So it has been a focus since we did these experiments, and also already in 2019 when we were looking at this problem, then it has been a focus to try to beat or to try to have the same performance of dynamic programming, but at the same time to do it at a lower computational cost. Okay, by the way, if you if you disregard shapes and you compute distances in between parameterized curves in this setting, then you don't get very good results. That's what we get. So this is a simpler approach, but it doesn't work. I hope that you see my colors here and my, is it all right? Okay, good. So let me go, this was my introduction. Let me go into more details of how we look at this. So as I said, shapes are unparameterized curves or surfaces with values on a manifold or on a vector space, depends on the application. One word of warning is that one should use shapes when it is natural to look at these curves independent of their parametrization. So that's the key, essentially. It's one of the important things to take into account, not use shapes if it's not reasonable. So here it's our definition. I will do this in the case of curves because it's easier to describe, is less technical. What we do is we start by a so-called pre-shaped space, and in our case, what we choose is the space of immersions. Here, I is an interval of the real line, is a subinterval of R, and we consider curves C infinity smooth, which have values in Rn. And we require that they have non-vanishing derivative. Okay. because of these constraints, because of this non-vanishing derivative, the space that we obtain is a manifold. In particular, it's an infinite dimensional manifold, Riemannian manifold. We can put Riemannian metrics on this manifold. But this is only the so-called pre-shaped space, the space of parameterized curves. And if we want to consider the shape space or the shapes, real shapes, what we do is we introduce an equivalence relations, and we say that two shapes are equivalent or two curves are equivalent if there exists a reparametrization that send one curve into the other. So if C0 is equal to C1, compose this reparametrization. And what is a reparametrization? Well, it's an orientation preserving diffeomorphism of I. So it's a map from, or it's a map from I to itself which preserve the order of points. And then the shape space is simply the quotient space of the space of immersions or the pre-shaped space and with respect to the diffeomorphism group. So this the set of equivalence classes. Okay, so this makes sense as a definition of shape, but of course one buys oneself a bit of trouble, because instead of dealing with simple curves, we now deal with the equivalence classes of curves. And then the distance, we need a good way of computing distances. In all the applications that have been introducing, distances are quite important. So we need to compute distances. We start by considering distance on the pre-shaped space. And I will discuss this in the next slide, how to construct this. But given that P is a Riemannian manifold, hopefully we have a good way of discussing or defining a metric on this manifold. And then what we do is we consider the distance on the shapes by simply taking the infimum over all diffeomorphisms such that the infimum over dp for all possible diffeomorphisms in this fashion here. So we take the distance between C0 and C1 reparameterized in all possible ways. So this makes sense as a definition, although one should think about if this is a well-defined distance on the shape space. And it's quite easy to show that this is a well-defined distance. And given that the distance dp, so on the space P, has this property down here, so it's reparametrization invariant. So the distance in between C0 and C1 does not change if I reparameterize with the same reparametrization both C0 and C1. So if I have this simple property, so if I am able to find this distance here with this simple property, then I'll have a good way of so this definition here makes sense. This is a good definition. And also my optimization problem will be not too bad, because I will have to deal with one reparameterization, reparameterize only one of the two curves and not both. Okay, here it's how to choose the distance on the pre-shaped space. So as I said, we will start by taking a Riemannian metric on the manifold of immersions or on the pre-shaped space, no matter how we define it. And then we will take as distance the geodesic distance in between curves in this space P. So here it's written here, the length of the geodesic between the curve C1 and the curve C2. So what we have here is depicted in this figure here in the middle. So this is done for a special choice, which of distance and of Riemannian metric, which I will define later. But what we have in this case, we want to compute the distance between this curve, which is a straight line, and this other curve, and they are both parameterized with parameterization the identity. If we change, so our metric will make a deformation of the straight line into this curve here. And this is the way it's deformed. If we change the reparameterization of the two curves, both reparameterized with a new reparameterization, but the same, then the deformation doesn't change, it will stay the same. However, if we change the deformation of the first in one way and of the second one in another way, then the deformation will change, and therefore also the distance will be different. So this is just to put things in place. This is what we need, but we shouldn't change, reparameterize the two curves in a different way. Okay, how to define the distance on the pre-shaped space is not a trivial task. In fact, the simple choices do not work. There are some famous papers of Mitchell and Mumford about this. If you choose the L2 distance in between the curves in the pre-shaped space, it doesn't work because you couldn't end up with the geodesic distance, which is 0, even for curves which should not have distance 0. So, but here it's the way we approach this, or the way many people before us have approached this. What you can do is to transform your curves first, to make a transformation, and then use the L2 metric to compare them. So, Alessandro, do you have a question?
So, because I think that the problem there is that you need to respect the quotient structure after. Namely, if the metric that you put in the pre-shaped space is not does not respect the structure of the space with respect to which you quotient it, then you're going to get something which is almost useless. Right? Is that correct?
Yeah, I think you're right, but this is a bit of a tricky business. So I think it's better to refer to the papers because there has been first some results, and then people have evolved on those results. I don't remember the details completely. But there is a paper or several papers by Breweries that one could have a look into if you're interested in the details. But definitely there are a couple of papers, at least original ones by Mitchell and Mumford, which are not straightforward to understand, in my opinion, but still maybe not completely impossible either. Okay, so the proposal is to first transform the curves in an appropriate way, and then to compute the L2 distance of the transformed curves. And the transformation is very simple. Here are two particular choices. The first choice here is the SRVT, is so-called SRVT, and the second choice here is the Q transform, so-called Q transform. So in the first case, what we do, we represent the curve by its derivative scaled by the square root of the norm of the derivative. And in the second case, instead, we represent the curve with itself, but scaled by, again, the square root of the norm of the derivative. So the first one is, I would say, easily generalizable to the case of Lie groups. This one is given for curves on vector spaces. And in the case of Lie groups, you can generalize easily this by replacing the derivative with the so-called logarithmic derivative in the Lie group setting, or the Maurer-Cartan form. And the second one instead is convenient, or we liked it because it's easy to generalize to surfaces. In fact, there is a generalization to surfaces of the first one, but there are some drawbacks, geometrical drawbacks, which are not do not work very well for. But both these two transforms have very important properties, which is that they are equivariant with respect to the two reparametrizations. And this is crucial because this implies that they are that the distance dp is a reparametrization invariant. And so we go back to this property here. So this allows us to have a good measure of distance on the shape space. Okay, what does it mean, equivariant? Well, it means that if I apply the transform to the reparametrized curve, it is essentially the same, apart from a scaling factor, as first applying the transform to the curve and then reparametrizing. Okay, this fact here allows us to rewrite the problem that of computing the distance on the shape space in the following way. We first transform the curves, and then we take the infimum over the diffeomorphism group of this new cost function. So the cost function can be written simply like this by using this equivariance property. So instead of taking the distance in between the curves in themselves, we take the distance in L2 norm of the transformed curves. The first is left alone, and the second one is reparametrized and rescaled, you can say. But the problem is that we are dealing with an optimization problem on an infinite dimensional space, which is this diffeomorphism group. In fact, it's an infinite dimensional Lie group. So we are not going to be able to implement this in a computer program or as an algorithm. So we need to at least discretize. So to replace this diffeomorphism group with a finite dimensional model, something in which something that can be computed. So as I said, we have an infinite dimensional Lie group. Its Lie algebra is the tangent space at the identity. And as I said, we need to discretize. So what do? Well, we choose a basis. We try to construct a basis of the Lie algebra, of this tangent space at the identity. This turns out not to be too difficult. Of course, we will not be able to compute the whole basis. We maybe have some formulas that tell us how all the elements of the basis look like, but we will have to truncate this basis. So we will take m elements of this basis, and this is a Lie algebra, so it's a vector space. So we can construct a finite dimensional subspace of the Lie algebra. And our approximation of the diffeomorphism will be given as a composition of L elementary diffeomorphisms, if we want, which are given as perturbation of the identity. So we take the identity and add an element into this tangent space here, which is given as a linear combination of the basis element, which I selected, so the first m of the basis. So these are vector fields. In particular, I will use this terminology later on as well. So what we're going to do here is, this is our ansatz of how the discrete diffeomorphism or the approximate diffeomorphism looks like. The beta values here are scalar values, and they are the parameters we are going to optimize over. So our optimization now is over L times M parameters, instead of being an infinite dimensional optimization problem. So we have a finite dimensional model, which is good, and we will see later on that increasing the number of composed elementary diffeomorphisms, and at the same time increasing the number of basis elements, will give us better and better approximations. So why is this a good idea? Well, there is some support based on theoretical results. We can in fact prove that if we make a composition of a finite number of diffeomorphisms of this type, identity plus FL, where FL is a one Lipschitz function, vector in the case of one-dimensional. In the case of the interval, is one-dimensional. In the case of the surfaces, it will be two dimensions, but in general, it will be a vector field. So we have the identity plus a vector field that gives us a diffeomorphism, given that the vector field is special enough. So, for example, we could take it to be a one Lipschitz vector field, which would guarantee that this map here that we obtain is invertible. So one Lipschitz in the sense that the Lipschitz constant of this f of FL here is less than 1, strictly less than 1. In that case, we will have a guarantee that the phi L is invertible. That's what we want. So the point or the problem or the question mark is, are we able to describe well the diffeomorphism group with the finite compositions of this type? And the answer is yes, at least in the case where we look at diffeomorphisms fixing the boundary of a compact convex set, or diffeomorphisms on the cube, which are cases which are interesting to us. Okay, before I go into that kind of detail, I will instead show you some experiments. And first, the case of curves, we need to choose a basis. And of course, the choice of basis is not immaterial. And here are three possibilities. For example, we can take a truncated Fourier basis. That's a very simple choice. Another possibility is these Jacobi polynomials, or another possibility is the Palais basis. It's similar to the Fourier basis, but it's orthogonal with the Palais metric, with respect to the Palais metric, which is given here. And here you can see in the pictures, you can see the first three elements of each of these three bases. So they look quite alike. So one wouldn't expect that they perform very different from each other. But we didn't compare too much. Here is the case of 2D problems in 2D surfaces. And we just take tensor products of the Fourier basis, at least in our numerical experiments. We have not explored much more. Let me show you the first experiment here. We compare two different methods, a gradient descent method, which looks like this. So it's very similar to our method, but it's an iterative procedure. We start with an approximation, phi n. The first step is the identity in that case. And we improve that approximation by also a diffeomorphism, which looks very much like the ones that we are composing together. But these coefficients here we have a learning rate eta, and these coefficients here, they are chosen so that we approximate as good as we take the best approximation of the gradient of the cost function. So the gradient of the cost function, to be perfectly approximated, we would have to use the whole basis in the Lie algebra, in principle at least. But here we just take a reduced basis, finite basis, and we want to make the best approximation of the gradient as possible, the Riemannian gradient. So this is a gradient descent algorithm, which is very reasonable to use. However, the performance is not very good compared to what we are doing. Of course, our computational cost is higher. Here we have less parameters for this gradient descent, but for us it was important to see that we could really improve on the performance of this gradient descent. Yes, Alessandro.
So I was wondering, have you tried to make M decrease with L? So what I'm saying is that maybe the first transformation is of a certain dimension, right? But then when you are very close, the dynamics maybe is, or the structure maybe is lower dimensional, because most of the job has been done by the first transformation, right? So maybe that way, somehow you save some parameters, and so somehow you do some sort of implicit regularization on the algorithm. So that's.
But I didn't understand what you said at the beginning, what you asked at the beginning.
So what I'm asking is, if you had experiments with M depending on L, namely
Yes.
M decreasing M with L. Let's say the first
I'm not sure
transformation.
I have exactly that experiment, but I have something similar, so it's coming. So here it's so what were we doing here? We have the same shape on the two cases, but with two one is reparameterized with the identity, and the other one with the non-trivial reparametrization. So we want to find the non-trivial reparametrization by our algorithm, and on the right hand side you see the gradient is, or the iteration which is given for our algorithm, how the error decreases, while this is the gradient descent, and there is some limitation. So the gradient descent is unable to capture the true reparametrization, while our algorithm is quite on top of the reparametrization, true reparametrization. So we were quite these were the first experiments, and we were quite pleased when we were able to do this. Here is another similar example. Again, on the right hand side, down here we see the gradient descent, or the descent of the error for the iteration in the parameters, and then the capturing of the up here is the approximation of the diffeomorphism, and we just trying to retrieve the reparametrization. Here it's more layers. We are using more diffeomorphisms, and the number of basis elements is also larger. The last example, the next example is on surfaces. Same type of example. We want to find the diffeomorphisms. On the left-hand side down here, you see the true reparametrization of the surface. In the middle, we have a surface, and on the left, we have the reparametrized surface, same shape, but different parametrization. And the algorithm is giving us this answer. So it's not perfect. If you can see there is, if you observe, you can see a little difference here, but it's quite good. I don't remember the number of basis elements. I don't remember this. Similar example here. Again, we can see that it's almost indistinguishable, at least at the naked eye, the reconstruction of the reparametrization. And here are the convergence plots that we were discussing earlier. So here what we see, we have different curves. We increase the number of layers or the number of diffeomorphisms composed, and we keep constant in each of these curves the number of basis elements. But going down from the top curve to the lower curves, we have increased the basis elements as well. And on the other side here, we have the same case. We increase in each curve the number of diffeomorphisms composed, and on the x-axis instead, we have an increase in the basis element. So what the top experiment is for curves, and the lower one is for surfaces. So what we see is that it's needed to increase both the basis elements and the layers in order to get a good performance. It's somehow, that's my feeling. I'm not 100% sure if this has some bearing. We didn't do analysis of convergence of the method, but this will come perhaps. But somehow it's a similar situation as you have when you do a discretization of a PDE. You need to, if your PDE is in space and time, you need to increase the discretization in time if you increase the discretization in space as well. So it's sort of related. And the next experiment is a deformation. Here we have taken two numbers, two digits in the MNIST database, 2 and 7, and we try to make sensible deformations in between these two digits. The first line here, it's a simple linear combination of the surfaces. So it's given simply like this. We have two surfaces, F1 and F2, and we take a convex linear combination, a very simple linear interpolation. The second line instead is done as follows. We construct the optimal reparametrization of the surface number 2 with respect to the Q transform, and then we make our linear interpolation. The reason why we do this in this form is that the Q transform is not invertible. In reality, what we would need to do is to make this reparametrization and then to make the inverse of the transformation. However, since the Q transform is not invertible, this is one of the drawbacks. This is not possible in this case, but still it performs quite well even with this approximation. Okay, I wonder if it's time for me to stop here.
You can keep going a few minutes if maybe another couple of minutes. So if you have if you need to conclude, yeah.
Yes, I think I'm going to just give up this this part on the theoretical justification. As I said, I mean, well, few words. What I can say is that it's interesting to, first of all, to restrict to problems or to diffeomorphism that fix the boundary. But this is, of course, a restriction, and there are some drawbacks. So, but if you can restrict to this case, then it's quite nice, because then the Lie algebra is the Lie algebra of vector fields that are zero on the boundary, and then the situation is nice because you have just one, you can cover the whole diffeomorphism group with one chart, which means that the manifold is not very nonlinear, and because of that, you can prove that, in fact, with the composition of a finite number of diffeomorphisms, even though you don't know how many, you can approximate well any diffeomorphism in the group. But and these diffeomorphisms you can choose to be one Lipschitz. So you restrict to take F to be one Lipschitz, so that you are sure that when you take the identity and add F, you get something invertible. For curves, things are simpler, but for more complicated situation, maybe they are not so simple. And yes, and then we extended this also to the case of the cube, a cube in D dimension. And it's a simple situation also I mean, it's a similar situation also in that case. So this gives us expressivity results. So if our algorithms are good enough, and if we choose enough parameters in our problem, then we are able to approximate well enough all the diffeomorphisms that we need to. Also, we have some bounds on the Lipschitz constant of the composition of these diffeomorphisms that in some cases can be good to have. But I'm afraid that these are quite pessimistic, even though, I mean, they are nice formulas, but they're probably quite pessimistic. That's it. I think that's all. I thank you for your attention.
Awesome. Thank you so much for the great presentation. So I've asked a couple of questions already, but are there questions from the audience? Well, I can keep going maybe with one at least. So in general, so you didn't quotient first with respect to let's say procrustes transformations. So you just went directly to quotienting with respect to diffeomorphisms. So I was wondering if there is any advantage to decompose things, namely you first quotient with respect to procrustes transformations, and then you quotient with respect to diffeomorphism quotiented with respect to those transformations, like some sort of the two-step procedure. So is there any advantage in doing that?
I'm not sure what to answer there. Probably you're right that in some cases it's I mean, my way of proposing this or to discussing this is trying to make it as simple as possible. And we have limited number of experiments. I don't have an army of people doing experiments on this, but I'm sure. But the tricks are fundamental. I mean, if you don't use the tricks, you will not get good results. So definitely, it's important how you pre-process things. And I remember that Marcus, for example, Marcus Esses-Blickler, he was doing some downsampling of the data. That was quite important in order to have a tractable algorithm, not to have too much data. Also, there were some assumptions, perhaps, which now I'm not 100% sure if they were used here or not, but in the experiments that I showed you. But you need, in some cases, to assume that the curves have been translated so that they have the same origin or something like that. So things like that I've not discussed. Probably they are important.
Another question that I had was related to SO3. So do you have also results on the special Euclidean group, namely when you involve
let me think. We did do a number of prepared a number of tools for that, but we didn't have an application where it was natural to do it, even though I would say that probably if you had the movement of animals, that would be more natural to use, because, well, or maybe even more detailed movement of humans, I would say, that probably SE3 is a reasonable. But another case where SE3 is very relevant is when we look at, it's a completely different setting. It's beam models. So we do have, for example, if you want to model cables, like the cable of your computer and movements of cables, and similar things, endoscopes or various devices where you have these long and thin and flexible structures, then there is a theory which is called geometrically exact beam models, and these they essentially the solution or the model for a rod like this is essentially a curve in SE3, a time-space curve, you can say. For each value of t and a spatial value, you will have an element of SE3. So that's quite interesting. We are also working on that, but not really from the point of view of shapes.
Awesome. Other questions? Nate, thanks for the talk.
Thank you. Thank you for inviting me.
So, yeah, if no other questions, let's thank Professor Celledoni again. Thank you very much for your great presentation. And I think next talk of the seminar is going to be April 20. But you know, you're going to receive our emails about it. So thanks a lot for your presentation. And then we can